So I did a little brainstorm, and here are my top 10 dirty secrets. I'm certainly not going to have time to talk about all of them. So what I've decided to do is go down a route which has to do with the Copenhagen interpretation, because we're supposed to be talking about observers here at this conference, right? So pretty much the only kind of interpretation of quantum theory that really takes observers seriously in any way, or says that they're important in any way, are Copenhagen type interpretations. So that's why I'm going to talk about those. The other things you can ask me about anytime you like during the conference. I can give a 10-minute rant on any of them probably. So let me start with the problem of quantum jumps. So as we know, Schrödinger didn't like quantum jumps. The problem is, though, he was wrong about what quantum jumps were. What he should have said is that the problem with quantum jumps is that quantum physicists are always jumping to conclusions. So, the point is, there is a serious point here, which is that a lot of people, a lot of physicists, when they start reasoning about the foundations of quantum mechanics, start treating it as if it's, I don't want to say this in a disparaging way, but pure philosophy or something like that. The way to determine the answer to this question is to use the scientific method. It's to construct rigorous arguments, mathematical theorems, predictions, experiments, and those sorts of things. And back in the 1960s, John Bell showed us how to do that for one particular type of question. But we're still very bad at doing that for other types of questions. And so I've just written here one example of a quantum jump that is quite popular at the moment. So we don't want to do that. We want to construct sort of rigorous scientific arguments about things. So the second dirty secret is that there is no Copenhagen interpretation. So why is this important? Well, for two reasons. One is, I think it's still the case that the vast majority of physicists in the world would say they subscribe to the Copenhagen interpretation. Now you can conduct a poll. We could all vote in this room, but I'm not going to do that because this is a completely unrepresentative sample of physicists. Many such polls have been conducted, and if you conduct a poll at this conference, you may find that the many worlds interpretation is quite popular. If you conduct one at a conference with a lot of Bohmians, you'll find Bohmian mechanics is quite popular. But really, the American Physical Society needs to conduct this poll, and then you will find that the Copenhagen interpretation is still very popular. Anyway, there is another reason why it's important that there's no Copenhagen interpretation, which is that we usually use it as a pushing off point for our studies of this question. We usually say something like, Copenhagen interpretation says X. X is crazy, so let me go and do something else instead. But if we don't agree on what the Copenhagen interpretation is, then that's pretty meaningless. So the Copenhagen interpretation is supposed to refer to the views of the founders of quantum theory. The problem is, if you read those, they're contradictory. They contradict each other, and they contradict themselves. Niels Bohr, in particular, is very hard to read. One of the reasons is that he seems to say statements which contradict themselves. Now, you may say, OK, but there's still some broad themes. There are broad themes, and that's what we're going to call sort of Copenhagen-ish interpretations. But still, you can't say that it's a fully coherent interpretation in its original form. Secondly, the questions that we care about today in Foundations of Quantum Theory weren't fully formulated back then. So you won't find answers to them. So for instance, if you read the writings of Niels Bohr, he never says anything about what is a quantum state, what do quantum states mean. He hardly talks about them at all, right? So there's no answer. So the interpretation is silent on that. The other thing is that it's very confused in the literature. So what is written in textbooks is often called the Copenhagen interpretation, and that's what people are often pushing off against. But that's completely different from this stuff and is also self-contradictory, as I'll explain in a minute. It's also often conflated with the shut up and calculate interpretation, which is sort of no interpretation. But it's extremely different from that. So Copenhagen, whatever it is, says some very, very radical things about the nature of reality. It doesn't say, I don't care, right? So we should definitely not conflate it with that. Okay, so in the rest of this, what I want to do is do an analysis of sort of what Copenhagen interpretations are and what they say about observers. And the conclusion is going to be that any Copenhagen type interpretation that's like viable has to in some sense be at least as crazy as the many worlds interpretation. Now this is going to be based on a recent result by Frauschiger and Renner, which I think is probably the most important theorem about observers in quantum theory, I don't know, maybe ever, right? So we should definitely be talking about it at this meeting. So what I'm going to mean by Copenhagen interpretations is going to be really characterized by three principles. I can defend in some sense that whether or not Bohr believed these things, I think he did believe something like them, but I really don't care in some sense. What I'm trying to do is put out a consistent kind of position. So two of the principles are this, right? So the idea is that, first of all, observers observe. This kind of interpretation is supposed to be built on sort of concrete empirical facts. The idea that when I do a measurement, the detector really does click, right? We don't deny that kind of thing in this interpretation. So we're going to say there are certain physical systems that count as observers. And this is not to say that observers are somehow fundamental or anything like that, right? It could be that environmental decoherence is enough to cause a definite measurement outcome, but all I'm going to say is that what we're doing is making an observation, well, an empirical observation. I know that when I go into the laboratory, which I rarely do because I'm a theorist, but if I go in and I make a Stern-Gerlach measurement, I see a definite outcome. So I don't doubt that that's what really happens, right? I also know that people like graduate students are very similar to me. So if I send my graduate student down to the lab to do that instead, then I'm not going to doubt the fact that he observes a definite outcome as well, right? So that's one of the fundamental principles. Observers observe, not because observers are necessarily fundamental, but because I know what it is to be an observer, and I can at least say that, that I think other people are observers too. Second principle is what I'm calling universality principle, which is the idea that anything, if not absolutely everything, can be described by quantum theory. Basic idea being there is no such thing as a fundamental divide between classical and quantum systems in nature. Now you may say this doesn't sound like a very Copenhagenish principle, but I will argue that I think it is part of it. So in particular, this means that observers are just other physical systems, so I can arrange a situation where I send my graduate student into the lab and and arrange a situation where I would describe him as being in a superposition. Okay, so those two of the principles. Okay, so before I move on to the third, I want to briefly, so I want to briefly talk about measurements, and then I want to dispense with the sort of textbook kind of Copenhagen interpretation. As most of us know, I assume if we apply quantum theory and we have the measurement postulates, if you start in a superposition state of, say, a qubit in one of two states, we measure it in the 0-1 basis. Measurement postulates say it collapses to 0 or 1. If we believe in this universality principle, then we can say, well, the measurement device is itself a quantum system, and we can describe that as an interaction. It would be an interaction something like this, where the initial state of the system gets correlated to the measurement device. So this is just a unitary operation which implements that, and then you see that if you apply that, you end up with a superposition of the two possible outcomes, and so that's usually what's stated as the problem of quantum measurement. But we don't actually have a problem here yet, because I haven't said anything about what these things are. I've just said, okay, there are two different descriptions, but what do these states even refer to? Okay. To make it a problem, you have to sort of adopt what it says in textbooks, right? So the textbook version of this kind of interpretation endorses something called the eigenvalue-eigenstate link, which makes this actually a realist interpretation. It's sort of, in some sense, about as far from Copenhagen as you can actually get. It says that isolated quantum systems actually do have objective properties. Those properties are the eigenvalues of the observables that the system happens to be in an eigenstate of. Okay, so once we have this, we immediately have a contradiction because this state has different objective properties than either of these two states, right? So this is just not self-consistent with the universality. Okay, so that's how you have that. This kind of interpretation is ruled out straightforwardly by the measurement problem. But that's not what Copenhagen interpretations say, right? So this is sort of my way of formulating it. I think they all adopt something which I'm calling the ineffability principle. So the idea is, first of all, we say that these quantum states, they don't describe a picture of reality. Depending on who you ask, what they do describe will differ. People might say they represent knowledge, information, beliefs, what we can say about a quantum system, advice about a quantum system. Different sort of Neo-Copenhagen variants use different terminology. But the important thing is just that they're not supposed to be intrinsic properties of quantum systems. Now, the important thing is if you're a Copenhagenist, then you also say that there is no deeper description of reality to be had. Okay, that's it. Right? We're just going to stop at this level of description. Now, the reason why you say that could be for one of two reasons. One is you could believe that quantum systems literally have no properties. So that would be the kind of position where the moon really isn't there when nobody's looking, which is fairly ridiculous. But the more interesting and reasonable possibility is that quantum systems may very well have properties. They're just ineffable. Okay? For some reason, whatever properties they have, it's fundamentally impossible to represent those properties in language, mathematics, physics, computer programs, pictures, whatever you like, right? So we're just positing that there's a limit to what we can say, not that those properties don't actually exist. I think there's a fairly strong argument that this was Niels Bohr's position, but again, I think, whether or not you like this kind of position, I personally don't like it very much. It seems to be at least a consistent position and one that's actually pretty hard to rule out. Okay. So this kind of idea is going to lead to what Arthur Fine, I think, called the shifty split. The point is that this idea of ineffability and universality are in tension with the fact that observers observe, right? So if we're going to say there's no way of describing properties of quantum systems in the quantum formalism, but I can describe everything, including observers in the quantum formalism, then I'm going to have no way of describing the fact that they observe something definite within the formalism itself. So to account for that, you're going to have to place a split somewhere between the observer, or classical system if you like, and the observed system, the quantum system. But this is supposed to be pragmatic rather than fundamental. It's not a fundamental feature of nature, it's just, to account for observations, you have to stick that in somewhere. So what that means is that there's going to be a hierarchy of levels of description depending on where you put the split. Okay? So we know that some quantum systems exhibit quantum effects, interference, and so forth. So there's going to be a lowest possible level at which you can place that split and still get the predictions correct. And there'll be a highest possible level as well. If you want to account for the fact that you actually observe something definite, then you've got to put that split in front of you. Okay? So, but there's a hierarchy of levels between this lowest possible level and just before the observer. The fact that these levels will disagree with each other on experiments that you're not actually performing doesn't matter in this sort of Copenhagenish type approach, because these aren't supposed to be descriptions of reality, right? These are just descriptions of something else, knowledge or something else. So as long as they agree on everything, on the experiments that we actually do, that's perfectly fine. Okay, so now we're going to start talking about observers and the problems with observers in this kind of view. So you might have thought, and I think probably, thank you, the early Copenhagen founders did actually think that it's going to be possible to find a level that all observers can agree on that will work, and that then there's going to be an objectively correct quantum state to assign, so that makes everything perfectly fine. But as soon as you contemplate actually putting an observer in a superposition, as in the Wigner's friend experiment, for example, so this is where you imagine that Wigner puts his friend inside a box, like the Schrödinger cat. The friend does a measurement, and then we're looking at the point before Wigner has opened the box. he's going to assign this kind of state to the system and his friend. But his friend, because in this kind of approach we have to account for the fact that observers observe, is necessarily going to have to put the split before himself. So he's necessarily going to describe the system as having been collapsed. Okay, so this kind of view is going to be impossible if you accept the universality. A more subtle point of view, though, is that, well, we've seen that observers may have to assign completely different states. So the quantum states are in some sense perspectival. They depend on the observer. But we could still say, there's still going to be an objective fact of the matter about what they've observed, even if we don't know it. So the idea is that when Wigner assigns this superposition state here, there's still an objective fact of the matter that the friend has observed as a definite outcome, and what that outcome is. It's just that since we're describing the friend as quantum, that's ineffable, right? Wigner has no way of describing it, so it's just not in his description. So this is what I would call an ignorance interpretation of macroscopic superpositions. And I think that a lot of sort of Copenhagen people, at least implicitly, endorse this kind of view. They think that detector clicks really happen. This is what gets ruled out by the Frauschager-Renner theorem. I have very few minutes to basically explain what this is. So let me quickly explain it. OK, so the idea is that what we're going to do is a mashup of the Wigner's friend experiment and a Bell's inequality experiment. And I should say that this is a version of the theorem which is due to Luis Mesanes. So the idea is that Alice and Bob are going to do a Bell inequality experiment, but we're going to put them inside a box, right? And outside the box is going to be Wigner, and Wigner is going to describe the whole experiment as a unitary coherent interaction. Because he's doing that, he can, in principle, because he's describing everything as unitary, he can, in principle, undo the measurements, right? He can go into the box and reverse whatever unitary interaction was used to make Alice's first measurement. So this is actually what he's going to do. Alice and Bob are going to make their first measurement in the Bell inequality test. Then Wigner's going to come in and undo those measurements. And then Alice and Bob are going to make their second measurements. That will all be described coherently and unitarily by Wigner. So it's a bit different from the usual Bell experiment. OK, so what can we say? So if we adopt this kind of ignorance interpretation, then we can say that actually there's a fact of the matter here about what Alice observed for the outcome of her first observable. There's a fact of the matter here for Bob about what he observed for his first observable. There's a fact of the matter here, fact of the matter there. Those things may be ineffable to Wigner, but they exist. These detector clicks exist. So if they exist, then we can make multiple runs of this experiment and also know that a relative frequency distribution for those clicks exists. Okay? So there is a probability distribution. There is a joint probability distribution over the outcomes of these four measurements. Okay? If a joint probability distribution exists, as Arthur Fine showed a while ago, well, many years ago, if such a joint probability distribution exists, then the correlations in it have to satisfy the Bell inequalities. Okay? Here, we're not getting that from locality. We're just getting that from the existence of these clicks. OK, so now what else can we say? Well, first of all, we can sort of just look at these two measurements here and say, well, we could have stopped the whole experiment here. We needn't have done all this bit here. So the statistics for these two had better agree with the quantum predictions. Similarly, we could have run this whole Bob experiment here, but stopped Alice's experiment here. And so these ought to agree with the quantum predictions as well. Similarly here, and similarly here. Right? So we end up saying that the marginals have to obey the quantum predictions. That means they're going to violate Bell inequalities. Right? So we have a contradiction. So the conclusion to this is that if you want to adopt this sort of Copenhagen position that observers observe and the universality principle, then you're going to have to come into this sort of fully perspectival kind of position. So when Wigner places his friend in superposition, we still want to say that there's a fact of the matter about the friend, for the friend about what they've observed. However, there can be no fact of the matter about Wigner, right, for Wigner. It's not just that there is a fact of the matter and it's unknown or ineffable to him in some way, but whether there is a fact of the matter about something has to be relative to the observer. So what we end up saying is that in this Copenhagen view, quantum theory has to describe individual perspectival realities. Happily, under normal circumstances, they tend to agree with one another because we don't typically put each other in superposition states, but nevertheless, fundamentally, those are different. Reality for me is fundamentally different from reality for you. So an example of a Copenhagenish interpretation which takes this type of view is cubism or quantum Bayesianism, which seems to be the only kind of view that's really left standing by this argument. I would like to make the comparison to conclude with many worlds, though, right? So I said I was going to show that Copenhagen interpretations are as crazy as many worlds. So in this kind of interpretation, there's no fact of the matter for Wigner about what his friend has measured, simply because for Wigner, neither of those things exist. In many worlds, if you consider Wigner outside of his box, the friend inside the blocks has split into two worlds. There are two copies of him that exist. There's no fact of the matter about which outcome the friend has seen for Wigner because he's not correlated with either of them yet. He's not in either of those worlds. So we end up with the same sort of crazy conclusion for sort of opposite reasons, either because neither of them exist or because both of them exist. But in some sense, this level of sort of perspectivity is one of the things that you might consider unpleasant about many worlds, if you consider it unpleasant. So if Copenhagen has to satisfy that too, that's bad news for Copenhagen. So I'd say that this is perhaps one of the biggest dirty secrets of quantum foundations, which is that an interpretation which is supposed to be based on the empirical facts of that detector clicks really happen, and that a lot of physicists would say they subscribe to, ends up having to be radically perspectival in this kind of way. So thank you for your attention.